Okay, for this lesson we're going to be looking at, oh, I thought it was about to fall over. We're going to be looking at flight mechanics. That's forces acting on an aircraft. We're looking at our Copeland text. The other textbook I have doesn't have much information on this. So the first example is level flight, and it's just looking at, and when we're talking about flight mechanics, we're talking about the forces acting on the aircraft in flight. This is level flight, so it's flying constant speed in at a constant altitude. Okay, level flight, straight and level. When you do a pilot's license, that's the first thing you learn how to do usually. Obviously, you learn how to take off first, but anyway, we're looking at the example in the book, and they have a dot in the center, and that's got C of G written on it. C of G, and that stands for center of gravity. So we talk about like distributed load, for instance, when we talk about representing it with a point force, all of the mass of that aircraft, if you wanted to just find a single point to run a weight vector through, that's where it would happen. Okay, so essentially if I wanted to balance that aircraft, I could balance it at that point. That's why it's called the center of gravity. So for this example, we have our lift force going up, and in Copeland that lift force is lift generated by the wing and the tailplane. And then going directly down, we have our weight force, which is W. And then through the center of gravity, they have thrust, which is the forward momentum, generated by the propeller. And at the back, running through the center of gravity, we have our drag. And obviously to maintain forward straight and level flight, our thrust has to be greater than our drag, and our lift and our weight have to balance out to maintain our altitude. So that's straight and level flight. There's a number of things wrong with that picture that in so much as it's very, very simplified. Okay, when we're talking about drag, that is a whole discussion in and of itself. But the thing that you might need to know about is that if you have a wing, we're talking about wings and how lift is generated, what tends to happen is your weight is acting straight down, but your lift vector is actually tilted back. It should be pretty much perpendicular to the chord. Now, as your angle of attack increases, as the wing starts to do this, and the wind is hitting it from this direction, as the angle of attack increases, that vector of lift is going to tilt more and more over. Okay, so you have a component of it which is going to assist you in overcoming the weight, a vertical component, and you have a component that's going to be horizontal, that isn't going to assist with lift. In fact, it's going to be a form of drag. Now that type of drag that results from that lift vector that's tilting back, it is called induced drag. So you'll see that term induced drag, it's actually a function of the lift that's being generated. It'd be lovely if you could just have a lift vector that's completely vertical and directly opposite your weight vector. But the way an aerofoil works, when we talked about this in our flight theories, both the classical one and the turning of air force, you need an angle of attack. So you're always going to have some induced drag that results from that angle of attack. So induced drag is one type of drag that you're going to have, but this term here, drag, they just said one word, drag, but it's actually a sum of both the induced drag, which results from the generation of lift, and a thing called parasitic drag. So induced drag results from angle of attack and production of lift. Okay, you can't have lift without induced drag. You try and reduce it as much as possible, but induced drag results from the generation of lift. Okay, parasitic drag, on the other hand, is when you get turbulent airflow. So if you create a really steep angle of attack, and this is the wind coming this way and flowing around the airfoil, if you do that, what happens is, and we've talked about this in the textbook, you get separation on the top surface of the wing. Anytime you have turbulence, that is called parasitic drag. Okay, so parasitic drag results from turbulence or turbulent flow of air over the aircraft. So an extreme version of that is obviously the stall, where you pull back on the stick and increase the angle of attack until the wind flow over the top fails and the aircraft drops. Now, if you were to put your hand out of a speeding car, which I say don't do, but if you were to do it, tilt your hand up, it goes up, tilt your hand down, it goes down. But if you tilt your hand back a long, long way, suddenly your hand drops. And that's because when it gets to a certain point, the airflow becomes turbulent and it kills all the lift. Okay, so that's what's known as a stall in an aircraft. If you're ever doing a pilot's license, when you're on the climb, your instructor's going to be watch the airspeed, watch the airspeed, watch the airspeed, because if it drops too much, you'll crash, you'll stall. Usually, if you're low and slow, it's a very dangerous situation because it takes a certain technique to recover from a stall, and if you don't have enough altitude, that's when you what the pilot says, you buy the farm. So parasitic drag results from turbulence. So stalling is one version of that. Another version of that is, we talked about wings, and a wing, this is a good opportunity to talk about winglets on wings. If you look at the end of a wing on an aircraft, you'll quite often see that the ends of the wing stick up. Okay, and you might say, why are those little things on the end of the wing? They are called winglets. And they are on the wing because from our study of lift, we know that we have positive pressure on the bottom and we have less pressure on the top. So we're going to say negative pressure or less. Okay, so more pressure on the bottom, less pressure on the top. So when you get to the edge of the wing, if we don't have this little winglet here, you're going to have air leaking over from the bottom to the top. And you might say, well, what's wrong with that? Well, as the aircraft moves forward through the air, you've probably seen it at the airport. You'll sometimes see coming off the end of the wing a swirling like tornado, okay? Coming off the edge of that wing, and that is caused by that leaking of the higher pressure air over the wing as it's passing forward. So as it's passing forward, air is leaking over and it's creating a wingtip vortex, it's called. So what we want to do and that wingtip vortex is turbulent flow. It's not streamlined flow. So it's parasitic drag as well. So what they do to try and reduce that from happening is the aircraft engineers have worked out that you put this little winglet on the end, and what it actually does is it's almost like a fence that stops that from happening, okay? And if it does tend to happen, it tends to happen above and behind the wing, okay? And it's a lot smaller. So you will still get a wingtip vortex, but it'll be a lot smaller. So think of it as being like a fence to stop that from happening, okay? Keeping in mind, of course, if you look at the whole wing, okay, the lift across the whole wing surface is not all the same amount, okay? If it was, it's not evenly distributed. If it was, you'd have high pressure differences at the end. You don't want that. So what tends to happen is wings are worked out so that you've got a shape that's kind of like that for lift. So you've got maximum lift happening, and it's decreasing as you get closer to the edges. So there's not that tendency for that to happen as well. But it still will happen, and that's why you have a winglet on the end to stop a wingtip vortex, okay? So that's what that is for. Sometimes, now the wingtip winglets are very common, and they certainly assist in both the climb and the descent most, in stopping those vortexes from happening. Some aircraft, the newer Dreamliners and stuff, if you look at the wing from above, it doesn't have a winglet, but the wing at the tip, at the end of the wing, sweeps back. So if you're looking at the aircraft from the top, its wings sweep back like that. So that is a swept back design. So this sweep back at the end of the wing does exactly the same thing. It takes that wingtip vortex, which would be out here, and it pushes it back behind the wing, okay? So it doesn't affect the wing as much. So the wingtip vortex becomes a lot narrower, and it gets pushed behind the wing where it's not going to create as much drag, okay? Both of these designs have been basically seen, you'll see a lot of seabirds that have this shape of wing, and it's a very effective thing for the cruise. So long haul jet airliners will tend to have a swept back design rather than a winglet, okay? But both are put in place to reduce the wingtip vortex and to reduce parasitic drag, okay? So what I want you to take away from this, is that you've got two types of drag. Induced drag, write this down. Induced drag results from the generation of lift, okay? You have to have an angle of attack to create lift. That causes the lift vector to tilt back, and therefore you end up with a vertical component which opposes the weight of the aircraft, and a horizontal component which is slowing the aircraft down. That's induced drag, okay? Because of the generation of lift. Parasitic drag results from non-streamlined flow of air, and it is in its worst case the stall of the aircraft if you have too high an angle of attack at too low a speed, or wingtip vortices. Two ways of stopping wingtip vortexes. One is the winglet, okay, which is that little fence at the end of the wing, okay, and it happens on both ends, okay. That is called a winglet. And the other one is a swept back design. Some birds have that configuration of their wing. Their wings are shaped like that, okay? You'll see it in nature. The winglet actually was inspired by another type of bird that has wings where the feathers on the end point upwards. And I think it's the gentleman's name, I actually can't remember. You might want to Google who discovered the winglet, but he discovered it via nature, very much like Leonardo da Vinci discovered a lot of things via nature. So many of the greatest engineering principles we know have been discovered through nature, okay? So this diagram here of lift, weight, thrust and drag, all at right angles to each other, is a very, very simplified example of straight and level flight. And you'll see in the book that we have some equations that Mr. Copeland has given us with that particular diagram. So we might just look at those equations. They're very much like the equations we've used for truss analysis and moments and all that sort of stuff. And those equations are well, there's just two of them. Sum of upwards is positive. Sum of forces vertical is equal to 0. 0 equals lift minus weight. Okay, that's how it stays in the air. Okay, and the other, that's equation 1 from Copeland. And the other equation he talks about is going forwards to the right is positive. Sum of forces horizontal is equal to 0. So 0 equals drag minus thrust. Okay, therefore thrust equals drag. Okay, so they're the two equations that he's given you. I think I said that the thrust had to be greater than drag. If you want the aircraft to accelerate, that would be the case. Okay, so if you just want the aircraft to be straight and level at a constant speed, all of those things have to happen. Okay, for a straight and level constant speed flight, and that was equation 2 in Copeland. Okay, so what have we taken out of this? I'm hoping that we know lift, weight, thrust and drag are all going to have to be equal, because we go, therefore lift equals weight. Okay, so both of those are equal to each other and opposite, and we know that it's a lot more complex than what's shown here. Okay, we know that later on we look at a more complex example of this. We know that the center of gravity and the lift are actually forming a moment. We know that thrust is never directly opposite to drag, and we know that drag comprises of both induced drag as a result of generating lift and parasitic drag, which is a result of turbulent airflow. That's the two differences between drag. Okay, so I'm hoping that you've now got a definition of parasitic drag and induced drag. I'm hoping that you know, you understand this very, very basic mechanics diagram for straight and level flight from Copeland. If you don't, pause it, copy it, read Copeland as well. Pages are written at the top of the board, and hopefully that will help you in the process. And we've done a little foray into the world of winglets and swept back wing design. Okay, and you know, you might want to supplement your studies with a little bit of research into the concept of a delta wing, which is used for higher speed aircraft as well. Anyway, that's me done for this part of the lesson. See you in the next video.